Hi and welcome to exercise 5 already from topic 2. And in this exercise we're going to investigate some properties of floating point arithmetic. So what's being asked? Write a program that takes two numbers, floats, as input, and the program outputs equal, just the word equal, if the sum of both numbers equals 0.3. Or not equal in the other case. So this is seemingly a very easy exercise. Okay, so let's see. 0.5 minus 0.2 should be indeed equal to 0.3. 0.3 plus 0 should be 0.3, and 0.4 minus 0.2 should be 0.2. So that's not equal to 0.3. So let's start with raising the question to get from the user two floating point numbers. Let's call them A and B. So I'm going to parse to a float whatever comes from the keyboard. So io.read, and I'm going to do this twice. Once I'm going to save the first number in a variable called A, or a const called A, second one in a const called B, because I'm going to change neither of those two variables. They might just as well be const. And then I'm going to check if the sum of both is 0.3. That's what's being asked. So if the sum of those two numbers, and again, watch me setting up the whole structure, the whole if statement at once. Okay, so if the sum of those two numbers equals 0.3, then I have to print equal. Otherwise I have to print not equal. Okay, so this is seemingly a very easy exercise. We just need an if else to decide if the sum of those two numbers equals 0.3. Now let's run the tests to see if this is going all right. And well, 0.15 plus 0.15 seems to be 0.3, so that's a pass. Again, 0.1 and 0.4 seems to be 0.5, which is clearly not equal, so that's a pass as well. But then we have something very strange, because expected should be equal, but the actual answer of our little piece of program here is not equal. So our piece of program answers not equal. Well, the test expects equal. Let's dive in. The test seems to add 0.1 and 0.2, and this should be 0.3, right? So let's go to the test. So if we see the tests here, okay, and clearly with an input of 0.15 and 0.15, I should have an expected output of equal. With 0.1 and 0.4, so with this input I should have an expected output of not equal, so that's okay. But this one doesn't work. So with an input of 0.1 and 0.2, I should expect equal, but our program gives a not equal. How is this possible? How is it that if A is 0.1 and B is 0.2, our sum doesn't seem to be 0.3? And if it's not, then what is it? Okay, so let's see. And you can actually debug the test as well. So you can choose to debug this specific test. Okay, and then we get 0.1 and 0.2, which are stored in A and B, and we are up for the next statement, and that's of course the test inside the if that's going to decide whether equal or not equal is going to be printed. Well, let's see. I have an A, that's 0.1. I have a B, that's 0.2. Sum should be 0.3, and yet our program claims that these two things are not equal. So let's then see what this sum is. Let's evaluate this expression, right? And there we have it. This the result of 0.1 plus 0.2 doesn't seem to be 0.3. It's a 0.3 with a lot of zeros and then a 4 at the end. What's going on? Well, in a floating point representation in computers, we have that we actually, I can explain this. If you have a number like, let's say, let's assume for a minute that our computer works with just digits, not zeros and ones, and we have, let's say, 5 positions to store a number. So this is a completely hypothetical computer, and this computer can store 1, 2, 3, 4, 0.45 as well. Then what happens is, since the computer stores each number with only up to 5 digits, with a small number like 1 point something, you have a high precision because you have 4 positions left for the decimals behind the comma, right? And if the number happens to be bigger, like 123, you only have 2 digits left for the fractional part. So that would mean, if we were to store numbers like this, that would mean that big numbers would be less precise in a computer than small numbers. And that's of course something that engineers who build all this never would tolerate. So what they do is they have an internal representation that is called as scientific notation. And they say, well, basically, we can write this number as 0.12345, and then we have to remember that we have to multiply times 10 to the power of 1. Okay, so I'm going to use this as power of 1. Okay, so 10 to the power of 1 is just 10 times this number gives me 1.2345, which is the original number. This number can be represented in the same way. So we're going to use all digits for precision, and we're going to store it as 1.345. So again, 5 digits for precision, but we have to remember where the point was. So we basically float the point around. That's where the name comes from, floating point. And I have to remember that I have to multiply it times 1,000, which is 10 to the power of 3. Now, the only thing that you need to remember storing these numbers in the computer are, of course, the precision digits, and these are called the mantissa, and this power of 10, which is called the exponent. Okay, so basically in a computer you have a mantissa like this, 1, 2, 3, 4, 5, because you don't have to keep track of the 0 point. That's always the same. Okay, and you don't have to keep track of the multiply sign and the 10 and the power sign. You just need to keep track of the 1. So let's say the power here has to be kept as 1, and as in the same way you could store this number with a mantissa, again 1, 2, 3, 4, 5, and a power of 3. So in this way, of course, we need extra room, we need space for the exponent, but in this small hypothetical example with only 6 digits, we would be able to store both this number, and the precision of those numbers would be the same. Now, because of this scientific representation inside computers, and of course it's called floating point numbers because it's not real numbers, they're of course finite in the fractional part, so that means we will have rounding effects. And that's why you cannot do ever the following 2 things. Don't store money in floating points. Never do that. how to solve this? Well, easy. You can just store cents. So store the amount in cents, and if you want to show it on the screen, you can always convert it to dollars and cents or euros and cents. Or you can use objects and classes. We're not there yet, but they could represent specific types like money. And in some languages you have what's called a decimal, like in C#, and that's a specific type that's not a floating point but a fixed point notation, especially for money. Second thing you can't do, so never store money in floating point, and never use equals or not equals with floating points. So you can't compare them with equals or not equals. You can, however, of course, compare them with smaller than, bigger than, smaller or equal, and bigger or equal. Okay. So you can use, however, use these. Okay. So what we're going to do to solve this problem, and that's the best we can do in computers, we're going to see if those two numbers we want to check for being equal are close enough together. And close enough together is going to be an arbitrary thing we agree upon, given some precision. We will say if they're close enough, meaning the difference is so small that it's smaller than some precision, then we'll call it even. Okay, so in this case my two numbers are this one, and so let's put it for a moment in some sum. Okay, sum of the numbers. Then I have the sum being compared to 0.3. I can never do that, so what I'm going to do is just make the difference and see if it's really small. And really small is something we have to decide upon, so let's add some zeros. Okay, this should be enough, but you can always have more. Okay, so we call this a precision, and we call them equal to some precision. In this case, a precision of 0.0001. Okay, meaning that the difference of these two numbers is close enough that it's smaller than this precision. Okay, that's the best we can do. So let's check this if this works. Okay. And we're okay. But be careful, because I can add something like this to show you what might happen. Okay, and I'm going to add another test here. Okay, mind negatives, I'm going to say. Okay, and let's say we have something that's going to be really big but negative. So let's call it minus 1,000 and minus 2,000. So the sum of these two will be minus 3,000, which is of course a lot smaller than 0.3, but not even close to 0.3. But if we look at the program, we're going to add this, and then we're going to add these two negative numbers. So this is going to be minus 3,000. I'm going to subtract another 0.3, which is going to be well, around minus 3,000.3, and this is a big difference. That's a difference of almost 3,000 between these two numbers. So nowhere will be minus 3,000 be near 0.3, and could we call it even? But if we look at this equation, it will be smaller than some small positive number, because these are negatives. So again, we're in trouble. Is this the one? Let's see. this should be not equal, of course. I'm wrong, okay? And then it turns red, okay? And of course I need to do it like this, minus 1,000 plus minus 2,000 should be not equal to, so this should be minus 3,000. Okay, and nowhere near 0.3. So what's happening is that the sum of these two numbers is going to be largely negative. And because of the fact that it's largely negative, it doesn't matter if you have some small negative added, the whole thing will be still negative, but largely negative, meaning that you have a large difference between our sum and the 0.3 that it should be compared to. And this is going to be smaller than some positive number. So I have to ignore the sign. That's what I need to do. And for that, we can use inside the math library some absolute value function that says to the program, well, we don't care what the sign of this two numbers, the signs are of these two numbers, but their difference should be small. And of course, if you subtract them and it happens to be minus a million, that's a big difference, but it's negative. So this is going to be turned in a difference of plus a million. And that's of course no longer small in this category, smaller than 0.0001. Okay, so again, we should be good to go now. Let's run all the tests. And this seems okay. So you need to take the difference between two numbers and compare it to something small. But beware of the signs, because if by accident this would be a large number but negative, it will be smaller than some small positive. So that's why we have to take the absolute value. Okay, minus 3,000 is nowhere near plus 0.3, and so the difference is largely negative, but if we take the absolute value, it's largely positive and it's nowhere smaller than something small. Okay, so we call this the precision. You could in fact add this to the readability view program and call this the precision. Okay, like this, and well, it aids the readability perhaps, and that's the best we can do. We can only compare floating point numbers in a way we basically decide if they're close enough, okay, if the difference is small enough. One more time I'm going to run the tests, and that concludes exercise 5 of topic 2.